All right, our last basic topic with electricity and circuits specifically, we'll be talking about power, which really corresponds to how bright something is when we're talking about lamps, but I guess it could mean something different with a resistor. What power means, power, as you might remember from the energy unit, is the rate of energy use per unit of time. Another way of thinking about this might be to think of this as, instead of energy use, the word we've been using is how much energy is being dissipated, which just means used. Okay? All right. So when we were talking about mechanics and energy, we defined power as so. Power is equal to the work done divided by the time, the energy used or the energy transferred over time. So we could write this as delta E over T. Since we know that work is force times displacement, we also wrote this as F times D over T. And since D over T is average velocity, we could also write the power as the force times the average velocity of something. Now, when we're talking about electric circuits, power takes on it's the same meaning, but the variables are different because none of these variables appear that much in circuits. I mean, you might have some delta E, but it doesn't really come up all that much. In electric circuits, you might have the following. P, the power, equals the voltage drop or the voltage change multiplied by the current. Now, that can be rewritten using Ohm's law, V equals IR, in the two following forms. V squared over R, in case you're not told the current, or I squared times R, in case you don't know the voltage. The total energy used by a circuit component would therefore be the energy equals the power multiplied by the time, since we know that energy, the amount of energy used, is equal to power times time from up here, which could be given as follows. VI times T, essentially any of the power equations multiplied by T. V squared T over R, or I squared R times T. Okay, that will tell us how much energy some piece of circuit has dissipated, has used. We're going to talk about two basic circuit elements that use up or dissipate energy. Resistors dissipate energy by turning it into heat. They turn this electrical potential energy into heat. Dissipate energy by turning electrical energy into heat. Light bulbs, on the other hand, do something slightly different. They dissipate energy by turning electrical energy into heat and light. And it's actually mostly heat that I believe that a light bulb gives off. It doesn't actually give off that much light, but since the light is more significant than anything else, we think of them as being bright. You know that a resistor gives off heat because if you have a resistor that's powerful enough, you can actually feel the heat being given off. I remember a couple of years ago, I finally touched a resistor that was in a circuit for the first time. Someone had the current, that was a very low resistance resistor. Someone had the voltage pretty far up, so that meant the current was pretty far up. And I touched it, and I actually felt the heat coming off for the first time. And I was like, oh, resistors give off heat. That's awesome. I had known it, but it was the first time I had ever felt it, and it was pretty neat. Most resistors, you wouldn't feel that, though. You would need a very high voltage. So let's look at some examples of brightness. Now, what I'm going to do is I'm going to draw, just because it's easier, I'm going to draw these circuits as having resistors in them, but you can think of them as being bulbs, and the AP sometimes does that, where they draw them. They're not real great with their drawings. So you can think of these as bulbs, okay? Determine, our job is to determine the power output of each bulb. Let's say that this is a 6-volt battery and we're dealing with a 3 ohm resistor here and a 9 ohm resistor here. Okay, we want to determine the power. Well, we do have the resistances for both of these bulbs, 3 ohms and 9 ohms, but what we don't know is either the voltage drops for them or the current. Probably the easiest to figure out would be the current, because this is a series circuit. The current is the same everywhere, so the current going through the 3 ohm resistor must be the same as the current going through the 9 ohm resistor. So in order to find the current, I already know the voltage drop for the entire circuit. I'm going to look now for the current, for the equivalent resistance, because if I know the voltage gain for the entire circuit, voltage gain or voltage drop for the entire circuit, if I know the equivalent resistance, I can find the current. Since this is a series circuit, I know that the equivalent resistance is equal to R1 plus R2, which means it's equal to 3 ohms plus 9 ohms, which means that the equivalent resistance is 12 ohms. And that means that the total voltage, the battery voltage is another way that I like to call it, is equal to I times Req. That would be 6 volts equals I times 12 ohms. Therefore, the current is half an amp. Now, figuring out the power is very straightforward. The power for the 3 ohm resistor, I know the current going through the 3 ohm resistor and I know the resistance, so I'm going to use this version of the power equation, I squared times R. So that is, let's see here, I squared would be 0.5 amps squared times 3 ohms. Let's see, 0.5 amps squared is 0.25. 1/4 of 3 would be 0.75, and remember, power is measured in watts. For the 9 ohm resistor, I can do the same thing because it has the same current going through it. 0.5 amps, we're going to square that, times 9 ohms. So this should be just be 3 times as much. I guess I'll do it on my calculator just to prove this to you. There's the first one, 0.5 times 0.5 times 9, 2.25 watts. Not 22.5, 2.25 watts. So the total power is equal to the power of both of these light bulbs combined. The total power is 3 watts. Okay? Now, what if we have the same basic components of the circuit, but we restructure it so that it is a parallel circuit? Will that change anything? Think about what you know about parallel circuits. And again, what we're going to do is determine the power output of each bulb. Think about what you know about parallel circuits. The current is not the same through these branches. However, you do know that the voltage drop should be the same in each branch because the voltage drop is the same in every branch of a parallel circuit, at least a simple parallel circuit like this. So, do I even really need to figure out the current? No, because I can use this expression to figure out the power. The power through the 3 ohm resistor is equal to V squared over R, which is equal to 6 volts squared divided by 3. 6 squared divided by 3 is 12, and that's 12 watts. For the 9 ohm resistor, we have the same basic idea. 6 volts squared divided by 9. That's 4 watts. The total power is 16. Okay? So, we see that typically there is more power use in parallel circuits. And what that boils down to really is the fact that there's usually a greater current through parallel circuits. I know we didn't find the current here, but if we had, we would see that the current was much, much bigger than half an amp. Okay? This is just one example, and this is a fairly basic example. There are many more tricky examples. Tricky examples. So get used to figuring out the power for certain things. I know we didn't do it a ton last year. I have one more example that I want to show you, and it has to do with motors and efficiency. And it comes up every once in a while. I think it's just a good thing to know. Even if it doesn't come up on the AP test, it's a good thing to know just for your kind of general use. Sometimes you'll get a problem that involves a motor, an electric motor, and it tells you information about the circuit, and then it asks you, okay, well, at what rate is the motor doing mechanical work, or figuring out the mechanical power. So if you know the voltage, current, resistance for an electric motor, you can determine how much work it can do in a mechanical sense, such as how much weight it can lift in a certain amount of time, which is kind of interesting. Let's do an example. The motor, let's say your motor uses a potential difference of 10 volts and a current of 0.05 amps. You see, and you test out, and you see that your motor can lift a 0.2 kilogram block a height of 10 meters in 50 seconds. Okay, you've tested that out. What is the efficiency of the motor? So we've got two kind of competing, not definitions, but two competing descriptions of the power output here. We have the power output that the motor is outputting. We have the power, the electrical power that the motor is consuming, essentially, because we know the potential difference and the current going through it. We also have the actual power, the actual output power, because we can figure out how much the energy of that block is changing as it gets lifted up. So I guess what I would call, in this case, the optimum power would be the power you get if you calculate, or the electrical power. In other words, what's going into the motor? P equals VI, 10 volts times 0.05 amps, 10 times 0.05 is 0.5 watts. That's the electrical power. That's the power the motor needs to run. What the motor is actually doing in terms of doing the lifting up, the actual power is the mechanical power. That would be the work done over a period of time, or another way of putting it, the force that's put on the object times the displacement over time. Or in this case, since, and I'm going to skip a bit of steps that or one or two steps that I would have made you, that I would like you to do. The force that it takes to lift up this object, and you can prove this very easily, is equal to the weight of this object. So when we're doing this, we're really looking for the weight, mg, times the displacement, how high it goes up, over t. The mass of this object is 0.2 kilograms. G, acceleration due to gravity, 10 meters per second squared. D is 10 meters, the distance it was lifted, and this happens in 50 seconds. 0.2 times 10 times 10 divided by 50. We get an actual power output of 0.4 watts. Now, why is there a discrepancy? Well, it's because the motor isn't 100% efficient. The equation for efficiency would be the actual output over the optimum output. This is how much we should expect. This is how much we're actually getting. And then we multiply that by 100. And we're going to get a percentage. The actual output was 0.4 watts. The optimum output, what we thought we should have got ideally, is 0.5 watts. We multiply by 100, and we get 80%. There's no such thing as 100% efficiency, but this motor has an efficiency of 80%. What this means is that 80% of the power generated goes into lifting the box, or the block, I should say. Well, what happens to the other 20%, you might ask? Well, the rest of it overcomes things like friction. It gets lost due to heat, etc. No motor is 100% efficient. So the fact that this is not operating at 100% efficiency isn't necessarily bad. It's kind of inevitable. So you're always going to have, because this motor has moving parts, you're never going to have a perfectly frictionless situation for your motor. You're going to have some things that rub against each other. That energy that's lost because of that needs to be overcome. As these things move, they get hot because of that friction. That energy that's lost to heat needs to be overcome. Okay, so that's why that efficiency won't be 100%. But that's a neat way to kind of compare and to relate back our study of electrical power and energy to mechanical power and energy, and a quick look at efficiency. So that is it for our electrical circuits notes. When you next see videos, they will be on the beginnings of rotational motion, which is kind of we're going to spiral back to mechanics for a little bit. We're going to be looking at some areas of mechanics that you have never looked at before. All right? I'll see you later.